So, good afternoon, everybody. Thanks for coming. So, my name is Massimiliano Sfragara. I am the Director of Product Management for NX Technologies. So, today I'm going to give you a brief overview of our ammonia chiller range. I will also show you an interesting case study that we did regarding a specific application of ammonia chillers. So a few words about NX Technologies is a world leader in natural refrigerants. So we have a range of products covering all the natural refrigerants, the most important ones. So CO2, ammonia, propane, and water intended as a heat transfer fluid. So we have more than 1,000 employees, 12 manufacturing facilities, and the companies within our group, they go back to 1934. So we have a very long experience in natural refrigerants. So a few words about the context. Why are we talking about natural refrigerants? I'm sure you are all familiar with the F-gas revision, but it's always interesting to highlight some of the most important facts. So you know that for the first time, the F-gas decided to phase out all the F-gases by 2050. So no more F-gases in 2050. Then, if you look at the bottom left chart, you can see that compared to the previous revision, there will be a strong reduction of quotas. So this means an impact on the price and the availability of the F-gases. And then, talking about chillers, there will be specific bans. So in terms of GWP from 2027, there will be a 750 GWP limit. And last but not least, a service ban from 2026 for all refrigerants above 2,500. So all these facts contribute to the movement of the market towards natural refrigerants. It's not only the F-gas, it's also the REACH regulation. So again, you may have heard about PFAS, but what does that mean? PFAS is a category of chemical substances, up to 100,000 substances, including many refrigerants, such as 1234ZE, YF, and all the compounds, including the YF in the mixture. And there is a considerable amount of evidence about the health risks posed by these substances. For example, kidney cancer, liver damage. So there is a proposal now under the REACH regulation to restrict the use of these substances. So we don't know for sure. The decision will be taken in 2025 according to the listed information. But in the worst case scenario, there might be a ban on F-gases even in 2030 or possibly in 2032. So that's why natural refrigerants are important. So let's talk about ammonia. For those of you who are not familiar, ammonia has been used since the 19th century. It's still one of the most used refrigerants in industrial refrigeration, especially for large systems above 1 megawatt. It's been historically used in pumped systems. So it means that the ammonia is circulated by a pump towards the users. And these systems have a very large refrigerant charge, so up to 4 kilograms per kilowatt. So you can have thousands of kilos of refrigerants in these systems. But more recently, we have developed low charge chillers. So low charge, you may have heard this word several times, but what does that mean? So basically, there is not an official definition of low charge. So for example, some people say below 1.3 kilos per kilowatt is low charge, but actually our system go as low as 65 grams per kilowatt. So and clearly when you have such a small charge, the safety is a maximum. So in terms of other characteristics, I will not go through this list, but what is important to highlight is that, yes, ammonia is toxic, but it's detectable at a very small amount. So just 3 to 5 ppm, you can detect a pungent smell. On the other hand, the tolerability limit, so when it poses a risk for the health, is much higher, is about 500 or 1,000 ppm. So there is a big gap, and that's why ammonia has been safely used for decades, mainly in industrial refrigeration. Also, I'd like to point out the material compatibility issue. So ammonia is corrosive for copper. So for example, if you think about compressors, it requires an open compressor where the electric motor, which has copper windings, is not in contact with ammonia, or a special semi-hermetic compressor with special electrical windings, for example, in aluminum or in coated copper. So this is an example of a concept we have developed. It's called a Mega. It's basically an outdoor industrial chiller, which is alternative to an indoor plant room, the traditional solution in the ammonia market. So you can see that is a chiller featuring industrial open screw compressor. And on top, you can see a very big evaporative condenser. The evaporative condenser is the most efficient way to condense ammonia because you have water in direct contact with the tubes where ammonia is condensing. So you can achieve a very low condensing temperature, even with with the air-cooled chiller, and therefore the efficiency is comparable to the best ammonia systems that you can build in a plant room. We also have the possibility to install direct expansion evaporators, which help to reduce the charge. So in this kind of unit, it is typical to have like 350 grams per kilowatt, so very low refrigerant charge compared to the traditional systems. And you can see in the left picture on the left, you can see an example of a real installation in a big industrial facility for an air conditioning application. So if we compare a traditional plant room with this kind of chiller, there are many advantages, but let's highlight 2 or 3 of them. For example, you don't need a plant room, so you don't need to go through the process of authorization to build an ammonia plant room, and this sometimes is time-consuming, can be very complicated, especially in certain countries. And then clearly, quality, because this is a plug-and-play system which is built in a factory and can be tested on site, so we can solve all the issues in the factory before the delivery to the customer, and fixing an issue in the factory is much easier and cheaper than fixing the issue on site, as we all know. So you may wonder what happens now if we need a more compact design, maybe with a better value for money, accepting maybe a lower efficiency. I don't need the evaporative condenser. Well, we have developed another range, which we call the Orca, which is basically a compact chiller for, let's say, light duty applications. So the main differences between these 2 chillers is clearly on the condenser side, because the Orca is a conventional air-cooled chiller. And also the compressor. The compressor is a semi-hermetic type, which means the motor is inside the casing, and it means there is absolutely no risk of ammonia leaks from the motor coupling. And clearly, the most important advantage is the low refrigerant charge. So you remember at the beginning I mentioned that we can go as low as 65 grams per kilowatt. So for customers who are concerned, who are not familiar with ammonia, and they are concerned about the refrigerant charge, this is the solution. So let's talk about one specific application. So as I said before, ammonia is well known in industrial refrigeration, but we believe in the possibilities of this refrigerant also outside this sector. And one example is data center cooling. So we decided to run a simulation with our internal simulation tools of a data center in Milan. So we made some assumptions. The water temperature between from 21 to 15, the climate profile of Milan, and the cooling capacity of 800 kilowatts. And we took two load profiles, 100% constant load and 50% constant load, which are two typical cases that can happen in a data center. So we compare all natural refrigerants and one synthetic refrigerant. And by the way, we have no conflict of interest because in our portfolio, we have all these products. So we are proud to be able to recommend to our customers always the best product for the application. In this case, so we considered air-cooled chillers with 1234ZE, with R-290 propane, with CO2, and with ammonia. For CO2, it was a split system. For all of them, we had a semi-hermetic screw compressor, except for CO2, it was a permanent magnet reciprocating compressor. So what we can see, let's have a look at this chart. So on the horizontal axis, you have the outdoor temperature. And be careful, the outdoor temperature is decreasing when you go towards the right. So you can clearly see that all the refrigerants exhibit increase in efficiency as the external temperature decreases. And this is pretty obvious. In particular, we can see that CO2 has a jump, if you look at the orange line, towards 15 degrees, because CO2 is changing from transcritical to subcritical cycle. But basically, ammonia shows the best efficiency in nearly the entire temperature range. So how does this efficiency translate in what is relevant to our customers, which is the energy consumption? So again, you have the outdoor temperature on the horizontal axis. You have decreasing temperature as you move to the right. And on the vertical axis, you have the energy consumption. So just remember that high is not good because it means higher energy consumption. So first of all, we can see in this simulation that the higher energy consumption is in the temperature bands between 19 and 25 degrees. This is normal, and this is expected because in Milan, there are a lot of hours in these temperature bands. We can also see, as we've seen before, that CO2, look at the orange line, CO2 energy consumption is decreasing, is becoming better than most of the other refrigerants for lower temperatures because of the subcritical cycle. But again, we see that ammonia shows the lowest energy consumption across nearly the entire temperature range. So ammonia, I'm referring to the green line. So how does that translate into efficiency? So let's have a look at the seasonal efficiency. Basically, it's the ratio between the energy, the cooling energy delivered during the year, and the absorbed energy. If we take 1234ZE as the baseline, because this is the most common refrigerant for data centers today, we can see that we have a slightly lower efficiency with propane compared to 1234ZE. With CO2, we have a very favorable performance at partial load. And this is because the system that we have simulated has 5 compressors and 1 circuit, so in part load is behaving very efficiently. But ammonia exceeds the efficiency of 1234ZE, so by 13 to 20%, depending on the use case, either 50% constant load or 100% constant load. So I've shown you all these numbers, but what is the message that I want to convey with this presentation is that ammonia has been known as one of the best refrigerants for industrial refrigeration. But in the context of the new regulations, and let's say to save the planet, we have to think about expanding the use of ammonia also in other applications. And one of them that we consider very interesting is data centers. But there are many others, even in large air conditioning systems or process cooling. When we're talking about large capacities, these chillers may be the ideal choice. Thank you.